Hello, welcome to Exida's webinar on using a spreadsheet to do an FMEA. It's my opinion that spreadsheets were one of the greatest inventions ever made, especially for the FMEA process. I know some of you will agree. Imagine doing an FMEA using paper forms, which I did at one point in the past. And when I got the spreadsheet, it was just great. I could copy paste, I could insert lines. We just remembered another failure mode. It's just great. Anyway, so I found for many years that spreadsheets were absolutely the best way to do an FMEA. I used them for many years. In recent times, I'm using an FMEA tool, which I happen to like even better. But today, our webinar is how to use a spreadsheet for a functional architecture design FMEA. And then we will compare it to an FMEA tool. This is part of our fall 2023 FMEA webinar series. I don't know if you got a chance to see the webinar on RPN numbers. What we're trying to do is explain how to get the maximum benefit from an FMEA for the minimum number of engineering hours. And we'll talk about that just a little more. Today, we're just going to pretty much talk about using a spreadsheet because it's a reasonably good way to get started. And if you don't have the budget for an FMEA tool, you really can get benefit from FMEA methodology, even using a spreadsheet. You can see we got some fun webinars coming up. I hope you can tune in for the whole series and learn a whole lot about optimizing your FMEA process. I know some of you don't know about Exida. We were founded over 20 years ago by a number of what I can call reliability and safety technical geeks, and that's something I'm proud of. Our primary work is in the field of functional safety, alarm management, and cybersecurity. I'm very proud that we started out with a pretty small company and we have grown to a relatively large global engineering company. One of the sister companies of Exida is the Engineering Innovation LLC, and they create engineering tools. You can imagine for functional safety, alarm management, and cybersecurity. There's a set of tools, a whole suite of different tools. You can see it on the top of your slide. They're called Excellentia, and that's primarily for systems level design in the process and machine industries. A second suite of tools called OEMX has a very different target. That's for new product or product development engineering. The objective of that tool suite is to speed up, improve quality, and maximize the benefits of methods like FMEA. The ArcX tool is the FMEA tool that's part of OEMX. Another sister company for Exida is the Functional Safety Certification Company, Exida Certification LLC. And we're also quite proud that we were able to build up to become arguably the world's leader in safety device certifications, certainly in the process industries. And we continue to grow in many different industries every year. We are technical geeks. I don't mind that term. I'm proud of it. But we do a lot of research, but we don't hide our work. We spread it around. We explain it. We explain it in our books and our white papers. in our training courses, and even in our webinars, which is why we're doing this today. Failure mode and effect analysis, FMEA. Well, based on my knowledge, this method has been around for decades, and it was created specifically as a design verification techniques to discover architectural design problems early in the development process. It has evolved into many different areas and under many different names. And in our previous webinar, we talked about at least a dozen of these new names because they're all variations on a common theme. And you can read the ASQ definition. ASQ is American Society of Quality, and you can see some of the breadth of application. But the primary and original purpose is design verification, finding potential problems in a design and deciding how to fix them. It's a very systematic procedure because we examine an architecture one block or element at a time. The concept applies to hardware and software. The concept even applies to cybersecurity. And it's good if you have a tool that can handle all of those particular fields. Now, we are going to be talking in our webinar series about design FMEAs. And what are all the objectives? Now, I told you we want to find the problems in a design. And we typically start with a high-level architecture and work down through if it is hierarchical, where a system is made from subsystems and so forth. And when we identify, we'll call it an issue rather than a problem, it's kinder. And if we have an issue that we don't feel is acceptable, what are the recommended mitigations? I mean, there's all kinds of things you could do. The objective is how do we fix a problem or perhaps show that a problem cannot occur? There's more than just that, though. In a good FMEA, we have to update the requirements as mitigations are chosen. Because if we want to add another automatic diagnostic or change the way a design has implemented, you've got to tell the designers that, and therefore it's a design requirement that has to be added. You need to define integration tests. Sometimes you can define a test that will show that a potential problem will not occur or will not occur with sufficient frequency to be concerned. An FMEA provides inputs to an FMEDA, failure mode effect and diagnostic analysis. Now the FMEDA, which you already know about if you attended our spring FMEDA webinar series done last April and May. If you didn't, all those recordings are still available and you can learn all about what is an FMEDA and how does it work. It is a component level analysis. It's not architecture, it's a component level analysis which predicts failure rates and failure modes. But an FMEDA, in order to be done quickly and accurately, needs certain information which should come directly from an FMEA. In the FMEA, we document the design choices we make. In effect, we document the design and the design choices, and often even you can see by looking at it what the rationale is for those design choices. And that's valuable documentation, not only for future designers, but for training new staff members. And it's valuable evidence if you're going to proceed with a functional safety certification or a cybersecurity certification. So we need to do all this. And we need to do it with the minimum engineering hours. I feel for that because it's so easy to overdo it. I've talked to people who spent weeks on an FMEA, and I think there's much better ways to do it. I did talk briefly about a hierarchical design and different design levels. At Exida, we use the term system to mean the highest level of interest. In other words, we can't define what a system is, and nobody cares for FMEA purposes other than we pick some point to start our analysis, and it's sometimes obvious depending on the context of our work. You can often have one level of subsystem design and sometimes two. And sometimes in some industries, an FMEA already goes all the way down to the component level. Now that's dying real fast because that really is a time-consuming way of solving that problem. And FMEDAs provide you with a lot more information than an FMEA. FMEAs have traditional roles. There's normally more than one person. I mean, here I've shown 4 roles. Often there are 4 people in the FMEA. Sometimes there's more. I've been in an FMEA where there was a dozen people, and I thought that was kind of overkill. And think of the engineering hours and the cost that we're burning up. But at minimum, in a conventional FMEA, you need a facilitator. An ideal facilitator is kind of a rude person who pushes you along to get things done, but that person must be highly experienced and have a deep knowledge of relevant failure modes and useful mitigation techniques. There's a scribe that keeps the notes of the meeting and completes the FMEA chart as we go. And normally we dump the FMEA report task on the scribe, especially those of us who don't really enjoy documentation. There's a design engineer who explains the design intent, and there's often a test engineer that is busy creating integration and validation tests while we're in the context of the design, where the necessary, especially the necessary integration tests become very clear. I said spreadsheets can and are being used. Now they vary depending on the specific application and the specific company policy and so forth. They can be quite complicated, as you see in this one example that I found on the internet. I can see this is a very special application. I see the words flight computer, so this looks like avionics. Spreadsheets can vary from the complicated to the simple. And I'm a proponent of the simplest possible FMEA spreadsheet that gives us the necessary objectives, that meets the necessary objectives. Perhaps better wording. This particular example has 4 columns in it, and I'm going to use this format for our example, our simple example today. You can add more columns as necessary, but be careful. Every time you add something, you got to spend time filling it out and thinking about it, and it could be a non-linear function of engineering time. What information does one need to start an FMEA? Well, in our case, for the architecture design FMEA, we certainly have to have a description of the system. Remember the design level of interest and its function. What is this thing and what's it used for? Often you will need a system context drawing showing inputs and outputs in order to understand the system and what it's supposed to do. At the system level, we need what are the system failure modes and a description of those failure modes, because that is the effect we're going to be entering. We certainly need a architecture design block diagram, typically for functional blocks and for hardware blocks, or a data flow diagram after functions have been allocated to software. Same technique for hardware and software. We must describe the functions of each block or each computing function in the software. And of course, if there are any planned automatic diagnostics or test methods, in effect, planned mitigations that have already been thought about, for which we already have requirements, we need to know what they are. Good set of inputs. All right. When we have that set of inputs, we will be able to generate the FMEA report, which describes and documents our analysis. We will be able to generate and should generate derived requirements. We should generate integration tests that we have defined, and it's highly likely we'll have to have some action items, which are unresolved issues to be decided later. And of course, the facilitator is the one who may call a halt to some of our debate and write it up as an action item. Now, let me give you where the concepts aren't necessarily always quick and easy to understand. And I've always learned best from examples. So let me give you a very simple example. This is what we call a flasher. It's a visual enunciation device used in fire and gas systems, in security systems. When there's a potentially dangerous condition, this device flashes an intense light, which warns people of the dangerous conditions. And of course, they respond depending on their training. We have some in our building. It's part of the security and the fire alarm system. It's usually accompanied by a loud siren. Oh, that siren is so loud, it hurts my ears if I'm near it. Anyway, there are people who don't hear, so we flash and sound. The function of this device is described. It flashes with an intensity of greater than 500 lumens when the flasher input goes low. And we have the flash rate and duty cycle. Okay, and I see a context diagram. I can see that the device is used with an external power supply of 24 volts, and there is a signal. It sources current, and the input goes high when the current is sourced, and the input goes low when the current isn't sourced. Okay, I can see what kind of an input is and how it works by knowing it's a current source digital signal. Now, based on that safety function description, it's pretty clear what the failure modes are. If the input goes low and this device does not flash, that's fail danger. If this thing starts flashing when the input didn't go low, that's fail safe. It's a failure. It's not supposed to be flashing, but it is, and that's pretty bad. If you're in an office building and all of a sudden, well, I think the sirens are worse than the flashing, but that's still really annoying when these things start flashing. And somebody's got to go figure out what's going on. Yeah, I've been in those situations also. Fail safe, fail danger. So what do we have so far as our inputs? The flasher function has been given to us. We have a functional description of the quote system, failure modes, and they gave us this nice little table of correct operation versus fail safe and fail danger. Good inputs. We're not done because we're going to do an architecture design. So I got to see the architecture, and here it is. I see basically 4 different types of function blocks, 5 blocks total, but the LEDs are the same, so we don't have to do the FME for those twice. We only need to do it once. And do we have a good, yes, we have a good description of the function of each block, which is really important because we're going to be identifying the failure modes of each block and the effect. And for anything that's fail danger, we probably ought to be thinking about what the mitigations are. So let's take our little flasher and try to do an FMEA with a spreadsheet. Now, we're not going to do it live today because it does take time to enter all this stuff into your spreadsheet. And if you're looking at this as a YouTube, I don't want you to get bored. So we'll start with the power supply block, and the most obvious power supply failure mode is we lost power. I mean, everybody's experienced that in one form or the other. That's indicated by the guide word of no. We've lost power. The output goes to 0 volts. Uh-oh. All those voltages we need to operate are not there. So what happens? The effect is the flasher will not flash. And it's pretty easy to determine the category. That is a fail danger. So right off the bat, we hit a fail danger, an effect with a fail danger failure mode. So I guess we better think a little bit right now about what a mitigation might be. The effect and failure mode category, we just type in failure will not flash, danger. All right, what are we going to do about it? I mean, failures occur. Can't do anything, can't stop them. So we brainstorm on that for a little while, and the facilitator pushes people to come up with ideas, and you brainstorm some more, and you think about the best idea of the ones you've got. Finally, somebody remembers, hold it. This is going to be used in fire and gas applications, and there's a standard that says we must have a redundant power supply. I'm not sure why that's the only thing that needs to be redundant, and I'm not sure why we can't just put in redundant flashers, but that's what the standard says, and we wish to sell to this market. So we're going to create a recommendation that redundant power is required, and we are going to add a diagnostic circuit to detect if either of the power outputs fail. Why? Well, anybody that knows redundancy knows that redundancy without diagnostics, reliability and probability models will show that the value of redundancy is not very significant unless there's a diagnostic to tell you when one of the redundant subsystems fails. There have been papers written on that if you don't know what I'm talking about. For the moment, we have a recommendation, and we used one guide word. We've got to keep going. What if it says more? That's the next one. Well, what if the input power or the output voltages go too high? Uh-oh, that doesn't sound good. Well, if the input goes too high, the transient protection should blow a fuse. And all we have to do then is replace the fuse. Obviously, that's a fail danger. The flasher will not flash if the fuse blows, but you know, Are we sure the transient suppression device can handle enough current to blow the fuse? What if the transient protection blows out open circuit and the fuse is still, that would not work at all. That would wipe out all kinds of electronics. I think we better make sure we've got a very good test for that. So we're going to recommend the power input circuit must protect against overvoltage without, we certainly don't want it to disable both redundant. Sometimes if it doesn't blow out the fuse, the failure can propagate to the entire power subsystem. We don't want that. Therefore, we're going to define a test. We'll define a very detailed test, but right now we've got to document the test objective and the need for a test. And so in most FMEA, in an FMEA spreadsheet and in many tools, we have to write up an action item to make sure we add the overvoltage power test to the integration test plan. No problem. If you have a separate action item system, you just have to launch the app, type in an action item with all the necessary information so we can remember where that came from, and then keep on going. The worst thing you can do is forget about it, in which case it may come much later in the development process with nasty amount of rework and redesign. Let's go to the next guide word, less. Well, the power voltages, one or more power voltages might be below specification. Well, if they get low enough, we know what'll happen. The flasher will not flash. I mean, there's got to be a range where it's working and then it stops working. We might run a test to see what that actually is, to see if we have good design margins, but hold it. We don't have to worry about this. If we get an output in one of the power supply blocks, the other power supply block will keep the system working properly. So the same recommendation is required for a low voltage and a zero voltage. I don't know that we need to specify. I think it would be so much better if we just merged the low voltage and the 0 volts into one. So we're going to cross this one off and change the upper one to output goes to 0 volts or below. Okay, good. Let's keep going. I couldn't think of anything with as well as or part of that apply to a power supply, and that happens with guide words. But I get down to the reverse and it makes me think, whoa, we did not have a requirement for reverse polarity power input wiring, should we? I mean, a lot of equipment today does have that, and to a certain extent, customers may expect it. And so we sit around and debate about that. And of course, what we could do is put a note in the user manual, be careful not to reverse the wiring. Of course, how many people read the user's manual? And if they did it, they'll still blame it on us. All right, what's going to happen? Well, the circuit will be damaged, and it could be damaged significantly, but it's most certainly a fail danger. And we're going to recommend protection against the reverse polarity power input be added to the design. It's a nice feature for the customer. Many of your customers will be happy as a result of that. Other than early, I'm not sure I can think of anything else right now in terms of failure modes. But we certainly have to create, and if you're using a spreadsheet, we have to create an action item to add these recommendations to the requirements for the redundant power supply, for the diagnostics, and for the protection against the reverse polarity power. And don't forget, we had one before for the overvoltage power test. All right, typically we do have to go into the action item application and enter these things and all the associated information so we know where this suggestion came from. We don't want it to get lost. We want the requirements to get updated so we can update our design and get the benefits of the FMEA. And this is a perfect time to remind you that, in my opinion, every development process is iterative. Imagine what we just witnessed. The problem is recognized in the first pass of the FMEA. We added new requirements. We updated our validation plan to cover those new requirements. Then we updated our architecture design in step 4. Then we have to update our FMEA and our integration test plan. And hopefully this time we won't find any more design changes, or we might and we iterate another loop. That's just development. So remember that when you're estimating your schedules. Developments are iterative. I used to estimate 3 passes per design task. And of course, the second should take less time, the third should take less time. But I always estimated 3 loops. I did pretty good after I started that. Although I had one engineer that worked for me who was really good, and he always did it in 2. And I always appreciated it because that gave us a little margin on our budget and our schedule, which do have a tendency to get used up. All right, let's take a look at our new design. We've got redundant 24-volt inputs with redundant conditioners and power voltage circuits. And you can see a new block down here, a power diagnostic circuit that will detect if either one of these individually fails, and a diagnostic output circuit, which we can use to tell the world that there has been a failure. I'll mention again, redundancy without an enunciated diagnostic doesn't have all that much value if you really sit down and analyze it carefully. Now we have a new architecture drawing. Definitions and the system level functions did not change, but now we have 1, 2, 3, 4, 5, 6 different kinds of blocks. And of course, our FMEA will get a bit more complicated, but we can use the spreadsheet. We can update the lines. We can add more lines. If we come up with more failure modes, we can insert. If we want to get rid of one, we can delete, and spreadsheets continue to do the job for us. There are FMEA tools. In fact, right now on the market, I think there's probably 24 different tools. I'm not sure, but every time I do a search on FMEA tool, I find a lot of companies, and some of them are very tabular, and some of them have configurable numbers of columns and so forth, and some are already fixed. The bottom line is there are a lot of tools out there, and these tools are designed to make things easier and faster than a spreadsheet. Some of these tools have error checking built in. Some of these tools have action item recording in the middle of your FMEA, so you can record action items and automatically track where it's coming from. And a lot of neat features to give you the benefits of FMEA without as many engineering hours. Let me show you an example. In this tool, you do an FMEA by entering the different kinds of blocks. And we've entered the power supply, the LED control, the power diagnostic, LED array input circuit, and diagnostic output circuit. And we do type in the function and describe the different blocks. And it is right now a hierarchical design, but it's only one level. At the systems, they called it a flasher. They called it an enunciator. I'll have to tell them we're using the name flasher now. Anyway, we have all the blocks entered. And for each block, now we want to go through and identify the failure modes. Now, one could be using guide words, but as I hope you're getting the picture, guide words can be time consuming. This particular tool has a list of predefined failure modes for every block type. Here's what happens. For every block, you identify the block type and hit the load subtree button, and the hierarchical chart, the tree diagram, loads in the failure modes. In this picture, they're a light blue color. I see they came up with a noisy power supply. They had low and high in case they're different income. In case they're different effects. I can see in the LED control circuit to power, those are good failure modes. And of course, what I like most is all I have to do to get them is to hit the load subtree button. That's right over here. Now we will be showing you more details about this later. Now what? For every failure mode, we need to detect what are any we have to define the failure mode in terms of dangerous or safe. And that's the potential impact without mitigation, which is lower down on the screen. You can put in the cause if you want, and if you're still stuck on using the equivalent of RPN numbers, you can do that. But right now, we're trying to get maximum benefit for minimum engineering hours. We're not going to bother filling in anything but the potential impact for each of these known failure modes. Then we load the mitigation. What do you mean load the mitigation? For every failure mode, this tool has lists of known mitigation techniques, which you may choose to use or you may choose to delete. And again, that gets automatically loaded when I press a button again. They want us to put in a low voltage monitor, and that is the diagnostic we choose. For high, we're not going to have any diagnostics because we have a redundant power supply. And an input blocking diode is a good reverse polarity protection mitigation method. So what do we got? We have our units, the failure modes, the failure mode effect, and mitigations. The recommend, but that's it. That's an FMEA. You can add more failure modes, you can add your own mitigations and so forth, but it's a way in which next generation tools really speed up the whole concept of FMEA. There is an action item and an integration test as part of this, and we have a number of integration tests defined and an action item to write a proof test procedure for inclusion in the safety manual. That popped out in some of the other mitigations that we came up with. And of course, that action item is already linked to the FMEA, and I'll show you exactly where it's all coming from. Now, the part of the tool that I kind of enjoy the most is pressing another button and generating the report. Of course, if you have a scribe, and it's, the scribe is usually the new guy, the guy who you can give the undesirable task to. I'm really not a big documentation fan. I don't enjoy writing reports, but I really do enjoy pressing a button and getting the report created for me. Boom, done. I conclude then and emphasize that FMEAs are valuable. Sometimes they're a little painful and sometimes they're a little boring, but FMEAs can be and are a very valuable technique to identify design issues, and often it is well worth it if you find one problem. If you don't find any problems, that's wonderful, and now you know that you can move ahead much faster. If you identify problems, you can update your design right now before you even start detailed implementation. A spreadsheet is a common traditional tool for use in FMEA analysis and will absolutely work. My recommendation is to keep the FMEA spreadsheet as simple as possible and eliminate any columns that aren't absolutely necessary to achieve your objectives. FMEA tools, including many from many different vendors, provide features to help prevent errors, reduce engineering hours, and reduce calendar time. Next generation FMEAs have built-in FMEA knowledge with failure modes and mitigations. And that's really pretty cool. If there are any questions you have or any comments you'd like to make, please do not hesitate to let me know. Right now, I can take time to answer some questions. I see one coming in. What's the difference between FMEA and HAZOP? Well, the simple answer is really nothing. HAZOP is the original word that came from the chemical industry creators, as the method was co-opted for design purposes in many industries and many levels of design. The term FMEA and the HAZOP word faded away and the term FMEA became dominant. And that's kind of where we are today. A functional FMEA is actually the same thing as a HAZOP, at least at the design level. All right, any other questions here today? Just see if I better double click on this. There it is. Just read another one. Is it necessary to do an FMEA on a component level? No, it is not. In fact, I don't recommend it at all. I recommend FMEDA instead, unless you don't care about failure rate, failure mode, quantitative predictions. In any case, you get a lot of benefit. It's very time consuming going down to the component level. You get a lot of benefit at the architecture design level. Is it much better with mechanical equipment which is influential to the process or the manufacturing process? Well, a process FMEA has some different objectives. Obviously, you're trying to find defects in the manufacturing process or in any process. But for mechanical designs, an FMEA is also valuable, and a mechanical FMEDA is valuable. But of course, as we learned in the FMEDA series in the spring, you do need a good mechanical component reliability database. Thanks for asking the question. Are there any other questions? I don't see anything yet. Let me just expand the screen to take a look. All right, I will. Is it possible to view the webinar later? Yes, yes it is. This Exida does record our webinars. We will typically post them and link the postings through the Exida website. You can also find most of them on the Exida YouTube channel. I go onto YouTube and I just do a search on Exida. I get the Exida channel and you can see many, many webinars that we've done, including all of the FMEDA webinars in the spring. Now, you will also get a summary set of slides from this. If you attended today, you'll get a summary set of slides. And you can also ask questions via email anytime you want. Remember, this is just part of our fall 2023 FMEA series. I hope you can tune in to the rest and learn more about streamlining and optimizing FMEAs to reduce engineering hours and still get most of the FMEA benefits. And in the last one, we're going to do a live demo of a hardware architecture microcomputer, a much more complicated example. And you can understand the benefits of a streamlined FMEA. Don't hesitate to contact us with questions. You can use the email address info@exida.com. And please take a look at our white papers and our YouTube channel. Stay tuned for the fall 2023 FMEA webinar series. Thank you very much. Goodbye.